Okay, let's get started. So this is the second part of our Bitcoin primer series. So if you missed the first part and you're watching on YouTube, I'd recommend you check that one out first on how Bitcoin solved the double spend problem. And today we're going to build off of that and look into a basic transaction structure and scripting. And so don't worry, you don't need to have a technical background to get this stuff. This is designed to be comprehensible to anyone. So my name is Mario Gibney, and I'm a customer support lead here at Blockstream. And let's dive in. So today there are going to be three parts. Today's webinar. Start with transaction building blocks. So basically, inputs, outputs, transaction hashes. We'll just see the basic structure of how they're built. Then we're going to look at basic scripting. So just different ways that you can send Bitcoin to people and encumber them. And then last, we're going to look at some very, very basic use cases for basic scripting, which originally were called basically the simplest types of smart contracts that you'll see. And if you're in the webinar, feel free to ask questions at any point in the chat group, and also pause at the end of each section, and we can go back and review something if we missed it. But yeah, let's get into it. So to start with, we're going to look into inputs and outputs. So just a quick review of transactions and their context. So as we learned last time, when there's a new block being added to Bitcoin's ledger, let's say a miner called Alice finds a new block and broadcasts it to everybody else. Everyone checks to make sure all the transactions are legitimate, and if they are, then everybody agrees, and that's the next set of transactions in the ledger. And this basically denotes, any Bitcoin that's moved from one owner to another. So let's look at this transaction number 2 here. Remember, the first one's going to be a Coinbase transaction, as we learned last time, but the second transaction, maybe it just indicates that this Bitcoin is going to go to a new owner, and it's going to get sent to someone new. And so we're going to look into exactly how that's specified in a transaction. So if we take a look at this transaction in a bit more detail here, it looks something like this. The basics of any transaction is going to have an input and an output. The input proves that the transaction can be spent by the person sending them and refers to an earlier transaction, and the output just shows who the Bitcoin is being sent to. Now, the one more kind of important piece of transaction we're going to talk about is a transaction hash, or TXID. You might have heard of this before. So just in case anyone missed the last presentation or you want a quick review, we're going to take a look at what a hash is. So a hash is just an algorithm that converts a string of data to any random-looking output. The outputs are going to be fixed length and deterministic. That means they'll always be the same length, and as long as the input is the same, the output will be the same, and it's one way. So you can't calculate the input from the output, but you'll always get the same output from the same input. So this is used in Bitcoin mining as well. If you need more detail on this, go back to the previous presentation. But the way it's used for transactions is that this allows you to make a kind of a fingerprint of the transaction. So you take all the data in the transaction, you push it through the SHA-256 hash algorithm twice, and then you get this transaction ID. And that way, each transaction in the Bitcoin network can be uniquely identified by its transaction ID. And we're going to take a little bit of a closer look at the output here. Now, you might notice I've highlighted it in gold, and that's because this right now is a UTXO. It's an unspent transaction output. So it's useful to distinguish between spent transactions and unspent transactions, because if you take all of the unspent transaction outputs in the Bitcoin network, that is essentially a list of all Bitcoin in existence and who owns them. And in the future, maybe Bob, who had this Bitcoin sent to him, will spend this transaction. So he'll create a new transaction, refers back to this one, and will spend it. And somewhere off to the right side here, we'll be sending that to a new owner. And once that happens, and that transaction gets confirmed in a block, then your original UTXO will become a spent transaction. And so if you're running a Bitcoin node and you're keeping track of all this, One of the important distinctions here is that your UTXOs, so a list of all the UTXOs is called UTXO set, and that's got to be kept in your computer memory because it needs to be referred to very, very quickly, so you can verify incoming transactions or new blocks. And then once it becomes a spent transaction, a spent output, then it can just be stored in memory because it doesn't need to be referred to as quickly. Or if you're running a pruned node, it can even be deleted later on. And then, of course, all transactions will have this chain where they always, any inputs refer to previous transactions, and any outputs, will presumably eventually get spent. And so the cool thing about this system is that you can, if you ever, receive a Bitcoin transaction, given enough time and energy, you can always go back and trace where it originally came from, and it'll always end up back into newly minted Bitcoin at one point. And so this is how the network keeps track to make sure that no new Bitcoins are artificially created or destroyed. So let's just say that that this purple transaction is the latest transaction in a new block that's been added. The earlier transaction it spends will just be a previous transaction, usually from a previous block. So it could refer to an output, from this transaction it's spending it. So the green transaction will be up here. It could also be an earlier transaction in that same block. So it could be could refer to an earlier one. But you can't ever spend a transaction from, you can't ever spend an output from a transaction that happens later, even if it's in the same block. So it's always got to refer to something previous. That should be pretty intuitive. No questions so far? No? All right. All right, and and again, just a helpful way to visualize this stuff. So whenever you have an output being spent in this transaction, Alice is signing this and sending it to Bob. We can just think of our UTXO set as denoting this Bitcoin owner being transferred from Alice to Bob. So now we're going to talk about multiple inputs. So let's say Alice received 2 different transactions from Carol and Dave earlier. She received 10 Bitcoins in some transaction earlier and 20 in another one, and she wants to send 30 to Bob. You can combine inputs, and so you can have multiple inputs with a single output, and it works basically as you'd expect it to. And then you can just visualize this as 2 Bitcoins being combined and being sent to a new owner. And you can also do the reverse. So let's say that Alice received a previous output of 40 Bitcoins, and she wants to send 15 to Bob and 25 to Carol. She can take her UTXO and split it into 2. And then this creates 2 new UTXOs, and they go to the new owners. So again, you can visualize this as you have a single output with a chunk of Bitcoin, and it's being sent to 2 new owners. So now we're going to talk about change outputs. So one of the important things here, you may have noticed that in all the previous transactions we did, you were never spending part of an output. You always have to spend the entire UTXO. So there's no count system. You can't spend like half of the Bitcoins in UTXO. You have to spend the entire amount. So what happens if Alice has this 50 Bitcoin output and she wants to send 35 to Bob? What happens is a wallet will create an extra output called a change output that sends the funds back to Alice. So again, it would look something like this. So you have Alice sending a Bitcoin and being split, and some of it being sent to Bob and some of it back to Alice. One of the main reasons that Bitcoin uses this UTXO model is for privacy reasons. A good Bitcoin wallet will always create a new receiving address. And so even though we can see, because it's an example, we can see that, this is Alice sending coins to Bob and back to Alice. The rest of the network won't necessarily know who the owners of these different addresses are. They'll just see coins being sent and to 2 new owners. Now, of course, this isn't perfect. There are kind of various ways that people can make guesses about what's a change output and what's not. And we're going to cover that in a future webinar when we talk about privacy in Bitcoin and where its weaknesses are, and some of the techniques that can be used to counter that. But for now, it's just change outputs are important concept to understand. Next, we're going to talk about our transaction fees. As we talked about in the last lecture, you need to pay some sort of transaction fee for a miner to include the transaction in a block. And this is never explicitly listed in transactions. So there's never any data field where you say this transaction has this many fees. It's always just implied. What you do is you take the total number of Bitcoins in the inputs and total number of Bitcoins in the outputs. You subtract the outputs from the inputs, and whatever is left over, that's understood to be the fees for the miner. So in this transaction, this would be a fee of 1 Bitcoin. You wouldn't really be paying a 1 Bitcoin fee. That's outrageously high. It's just easier working with whole numbers here. Normally, transaction fees are in the several hundred or several thousand Satoshis. But yeah, this transaction technically would have a 1 Bitcoin fee. And same thing works if you have multiple inputs and outputs. Here, there are 72 Bitcoins in the inputs and 70 Bitcoins in the outputs. So that would imply a 2 Bitcoin fee that would get collected by whoever mines the block that this is included in. And so just so we can see how that works, you may remember we have these coin-based transactions. And so all of the fees from any transactions get included in that one. And another kind of exceptional thing about coin-based transactions is that they are they're the only types of transactions that don't follow the regular rules in terms of inputs, because coin-based transactions are a way to spend both newly created Bitcoin and transaction fees. They don't need to have an input. It doesn't need to come from somewhere. So, that block would have had 13 Bitcoin for the miners. That means 12.5 Bitcoin from the block subsidy, that is newly minted Bitcoin. And in this example, all of the transaction fees and the rest of the transactions added up to 0.5 Bitcoin. So that's 13 Bitcoin for the miner. So here we're just, it's going to be a helpful way to think of the UTXOs. So on the right, we can see, new blocks in Bitcoin's blockchain, and these little white bars are going to be our UTXOs. So those are any outputs that haven't been spent yet. So let's just let's look at what's going to happen if a new block is added. So all these outputs are going to be represented here as these little coins with their owners. A new block gets added. So there's 4 transactions here. Realistically, blocks are going to have many more than 4 transactions, but we're just working with small ones for now. So this first transaction might show this Bitcoin here being spent. So that gets sent to a new owner. And so we can say that maybe it was spending this UTXO up here from this previous transaction. So once that gets added, this coin is no longer owned by that owner since it's been spent. So that UTXO could be forgotten about. So we still know that there's an output there, but we don't need to remember it because it's now owned by someone else. And then let's take a look at this next transaction. Let's say this one has 2 inputs and 1 output. So you might see those 2 Bitcoins being combined and sent to the new owner. And then those could be UTXOs from 2 different transactions in previous blocks. So those 2 UTXOs have now been spent by this new transaction. So the UTXOs can then just go with the rest of the history. And then we'll do another example of, let's say immediately after receiving this transaction, this person wanted to send to 2 new outputs. And so then that Bitcoin gets split into 2. Maybe one of them is a change output, maybe not. And then that spends the previous UTXO. So that one's, again, forgotten about. And now we've gone through almost all the transactions. So we'll talk about the Coinbase transaction last. Remember, this is newly minted Bitcoins. This doesn't come from anywhere. This just pops into existence as a reward for the miner doing their job. So that's going to be newly created Bitcoin and any of the transaction fees from this block. And so now we have our new UTXO set. And so next time a block gets added, you go through the same. Your node will go through the same process, and you'll know the new kind of ownership of all the Bitcoins on the network. Right. There's one question: are transaction fees from block production also locked for 100 blocks? Thanks for answering that one. Yep. So there's a quick question about that. Coinbase transactions, the miners cannot spend them right away. They have to wait 100 blocks. There are a few different reasons for this, but it's mainly to disincentivize some sketchy behavior from miners. But yeah, that applies to both newly created Bitcoin and to transaction fees that have been collected. Easy to remember that is if we go back a bit, you can see in our Coinbase transaction, it all comes out into a single output here. So there would be, you don't have a separate output for your newly created Bitcoin and for the transaction fees. It all goes into one output. But that was a good question. Thanks for that. All right, skipping ahead. So basic scripting. So far, we've only been talking about a very, very simple case where when you send transaction to an output, it goes to a single owner and they can spend it. But we're going to see that there are a bunch of different things you can do. So let's just look closely at this UTXO here. So this is your basic type of transaction. It can be spent by Alice's signature. And there are a few. If you ever heard of opcodes, that's a bit deeper than we're going today. But this, again, is not quite as simple as just saying Alice can spend it. There are a few different operations that go on there. But the basic result is that if Alice can sign this block or sign for this transaction, she can spend this output. So other things you can do, you can have multiple signatures, which we generally abbreviate as multi-sig. So you can have n of n, meaning you have a certain number of valid keys, and you need each of them to be signed. So these 10 Bitcoins might be sent to Alice, Bob, and Carol, and all of them need to sign it in order for it to get spent. You can also do a K of n multi-sig. So instead of 3 of 3, you have 2 of 3, meaning any 2 of these parties can sign, and then they can spend the transaction. You can do something like revealing a secret number, like a pre-hash. So this is another way to use hashing algorithms. Because they're one way and you can't figure out what the input is from an output, you can provide the output of a hash algorithm and say, you can spend this Bitcoin if you can produce the input that produces this hash. So it's just a way of keeping some sort of secret. You can combine the different spending conditions. So this might require Alice's signature, and she might need to provide the pre-hash for some output X. You can also do a time lock. Time locks are pretty interesting. There are a variety of types of time locks in Bitcoin. We're just going to stick with one type today called relative time lock, check sequence verify. So this basically means a certain number of blocks must pass before you can spend this. So in this example, we have a 144 block time lock. So that means this output couldn't be spent until 144 more blocks have been created on top of it, and then Alice would need to sign it. 144 is roughly 1 day's worth of blocks. The other thing you can do is you can have either or spend conditions. So in this output, it's been dictated that either Alice can just sign and spend the Bitcoin at her choosing, or Bob could sign for it and send the Bitcoin where he wants after 144 blocks have passed. So now let's look at some different, possible use cases, because this is all a bit abstract. So what could you do with these things? So you could do an escrow type of scenario. So let's imagine that Alice and Bob want to make some sort of bet. Let's say they're betting on the outcome of a football game, and they don't quite trust each other, but they trust their mutual friend Carol. So what they say is, all right, we're each gonna bet 20 Bitcoin on the outcome of this game, and we'll send it to this output. And the way this works is that once the result is shown, so let's say Alice wins the bet. In case Bob doesn't cooperate and refuses to send all the money to her, Carol will presumably, as the trusted escrow, provide the second signature needed to spend those funds. So, now a bit of an error here. So this should say A, B, and C, and any combination of 2 of them could send them to Bob here. And then, of course, the output gets spent. It's no longer an unspent transaction output. It's basic 1, and this is the new UTXO. You could also do something like shared funding of a project. So let's imagine that maybe Alice is some sort of some wealthy funder, and Bob, Carol, and Dave come to her and say, "Oh, we've got this really great project. Do you want to funded for us. We need 35 Bitcoin. And Alice says, okay, well, I'll do it, but you guys need to all agree on how the money gets spent. So Alice sends them the Bitcoins, but on the condition that if they can't agree on how it gets spent within 30 days, then Alice will take it back. So in this scenario, Bob, Cal, and Dave have 1 month to spend the Bitcoins. If they don't, Alice will be able to spend it. So again, 4,320 blocks, roughly 30 days. So if they do all cooperate, they can send it, to E's account and spend it all right. If not, Alice can sign for it. And just keep in mind, in case it's not already obvious, when either one of these conditions is spent, then the whole UTXO is done. So once Alice has done this, Bob, Carol, and Dave cannot spend it later on. So it's just a good rule of thumb to remember that you can always spend the entire context of a UTXO, never part of it. Do you have a question coming in? So lastly, we're going to, oh yeah, it does seem very useful, Rowan. We're going to take a quick look at how we use this in one of our products, Blockstream Green. Some of you may have used our wallet before, and so we're going to take a look at how we can provide some extra security using a multi-sig. So in this scenario, we'll say our user is U, and G is for our service, the green servers. So what happens is, the user creates some sort of wallet, and in its receiving address, it'll have this type of spend condition. Now, keep in mind, this is a slightly simplified version of how Green works today, but this is essentially the type of structure it uses. So when funds are sent to the user's wallet, there are two different spend conditions. The first is that the user and the Green servers can both provide their signature to spend the funds, or the user can provide their signature only after a time lock, after a certain amount of time has passed. So in this scenario, that's about 6 months. So what this allows to happen is that the Green servers can provide 2FA security. So you can have some alternate confirmation you need to pass, like an email or Google Authenticator, and then the Green server will provide the signature needed, and then you can spend the funds, just like this. Then 35 Bitcoin gets spent and gets sent to Eugene or whoever. Let's say something happens, like the user loses access to their 2FA methods, or the servers become inaccessible. Then the user can just wait for 6 months, and then can spend the funds unilaterally using the second condition here. Now let's. You can also imagine what if the user only wanted to spend part of the funds, not all 35. Like they wanted to send 20 Bitcoin to someone, their wallet would create a transaction like this, and this would send 20 Bitcoins to Eugene, and then 15 goes back in a change output. So you can see the change output here is the same structure as this previous one, and then it starts a new time lock, and you have the same level of security again. And just a quick taste of what's going on for the next lecture. These are actually the only building blocks you need to get Lightning Network working. If you haven't looked into Lightning Network yet, if you've heard people explain it, it seems really, really complicated. It can be a bit tricky, but all you really need are this combination of multi-signature and pre-hashes and time locks, and then you can create these channels. So we're going to go into this next time, but this is actually a commitment transaction for updating the state of a Lightning Network channel. So we're going to take a look at that next time. And in the meantime, does anyone have any final questions before we wrap up for today? All right, we got one coming in. Okay, yeah, thanks very much for chiming in. And I think we're going to call it a day. All right, take care, everybody. And I know that one was a little shorter than the previous one, but the next one should be a lot longer, has more details in it. So thank you very much for coming. Take care, everybody.